So today we're going to talk about trends on the periodic table. So we are going to label these notes periodic trends. Okay, the first trend that we're going to talk about is atomic radius. So we'll just go ahead and start these notes out. Atomic. So when we look at this word, the first thing we always try to think about, what does the word mean? Atomic, having to do with atoms. Radius. What do you think of when you think of the word radius? Hopefully you think of a circle, and half of the circle is the radius. So an atom, okay, that's a terrible drawn atom, but we have an atom, we have radius, having to do with the atom. We think about radius, that's telling you something about the size of the circle. So atomic radius is the size of the total atom, including the electron cloud. Including the electron cloud. So in the lesson today, I put this picture, just Googled it, found it on the internet. So on this picture, we can kind of see the atomic radius trend if we just kind of look at it and digest it. If we know that we're talking about circles, radius is half the circle. Let's take this down to its most simple form. Where do you see the largest circles on this periodic table? Down here. Cesium 55 is what this one, the largest circle on this picture is. The smallest circle is up here. Helium. Little tiny helium. So which way does the trend increase? The trend, the atomic radius gets bigger as we go from right to left and from top to bottom. Now that is counterintuitive. That is not like we would guess it would be. So the atomic radius trend goes like this. It gets larger as we go down and larger as we go back to the left. So let's go ahead and put that in our notes. We are going to draw, to the best of our ability, a periodic table. Okay. And then let's note the atomic radius. I wanted to talk about this one first because it does kind of go the opposite way that we might guess. Okay. So atomic radius increases as we go down and to the left. So we're going to make that very clear. Down. And we'll write also bigger as we go to the left. That is, this is the one that kind of goes against what we would think, against what we would guess. So the largest atoms are over here, and the smallest atoms are up here in the top right hand corner. Okay. We want to make sure that we are thinking about this as we go along. This electron cloud, including the electron cloud, has a big impact on radius. You can kind of see as we go down this first family here, get largest here. Why is that? Why do we see that trend? This is the first period, the second period, the third period, the fourth, the fifth, the sixth, and so on. So we have more orbitals, we have more energy levels on this atom, even though cesium has 55 protons, those 55 protons kind of lose their pull once that cloud gets so big and those negative electrons are so much farther away from the nucleus. And that has a big impact on radius, is the distance from the nucleus. All right. So let's do a little test. We'll look at The periodic table, bring that in. If we're looking at atoms, size, atomic radius, which is bigger, nitrogen or oxygen? Oxygen's bigger. Okay, which is bigger, nitrogen or phosphorus? Phosphorus is bigger. Let's go a little farther apart. Which is bigger, sulfur or indium? Indium is bigger. Okay, what about the same period, which is bigger? Selenium or gallium? Gallium is bigger. Okay, so be sure that you can answer those kinds of questions. And let's go ahead and talk about the next trend that we see in the lesson. I posted a video. It's a pretty good video. It's very short, so I would encourage you to go and look at that from Teacher's Pet. It's a pretty great channel. She does a great job of breaking it down. So electronegativity is the next trend that we're going to look at. We can see electron right here in the first part of the word, so we're going to note that. And this negativity part, don't let that mislead you. We are talking about how much an atom wants electrons. That is chemistry according to Candace. So however, it's the electronegativity is the affinity of an atom to attract electrons. So it's getting those electrons to it is where electronegativity comes into play. We are talking about making bonds. We're also talking about kind of getting those electrons to the atom. So let's draw our quickly becoming infamous periodic table. And let's discuss just a little bit. The first thing we need to think about, if we're talking about bonds and making bonds, we're going to single out the noble gases right here. Okay? Noble gases do not have values for electronegativity. So let's write that down. Why do you think that is? They don't make bonds. So they're not wanting any more electrons than they already have. All right. So let's think about this trend. If the noble gases are stable and all atoms want to have an electron configuration like the noble gases with a full outer shell, which atom is the most electronegative? Fluorine. Fluorine is the most electronegative, so we're going to go ahead and make a big note of that. Fluorine is the most electronegative. And then we will look at which one is the least electronegative. Francium is the least electronegative. And you can't see what I'm writing. Well, okay, so which way does the trend go? Okay, the trend is an intuitive trend. It goes up and to the right. Okay, up and to the right. So we should probably make note of that. Electronegativity increases as we go up, and it increases as we go to the right. So those are very intuitive, the way that we would normally look at it, trends. But let's kind of combine these two, and let's think about how these trends work together. If we look at fluorine, and we bring back our periodic table, okay, what period is fluorine in? 1, 2. Fluorine is in the second period. So if we're using a Bohr model or the planetary model to think about these atoms, we would have something like this. Fluorine has the first inner circle, and it has the second. Okay, so the 9 protons in the nucleus of the fluorine atom have a really good pull on these electrons in the outer ring. They're very close. They also have a pretty good pull on electrons out here, outside of their own electron cloud, because it only has 2 rings. When we look at francium, let's consider our friend francium. Okay, let's look at our periodic table. Francium is in the 7th period, so it has 7 energy levels. Let's look at that. So we have our first one, we have our second one, third, fourth, fifth, sixth. We're just getting in everybody's space here. 7. Okay. Yeah. So when we consider francium has 87 protons, so that positive charge is pulling on all of these electrons. However, there's a pretty big space between the nucleus and the outside of the electron cloud. So this electron out here, francium doesn't have the hold on these outer and other electrons that fluorine does. And so this explanation kind of leads us to ionization energy, and these two can be kind of mixed up and intermingled in student minds sometimes, so we'll kind of discuss the difference between those two. But the idea here is this distance, okay? Because francium is such a large atom, the distance between the nucleus and the outside edge is pretty big, so that positive pull on those negative electrons kind of loses its beef. Alright, so there's a couple of bonus features that we need to think about for electronegativity. I know, bonus questions and bonus features, they should be fun, right? But one of the bonus features is similar electronegativities, so atoms with similar electronegativities. And we're going to say this right now, and then we will come back to it in gross detail later on. But similar electronegativities form non-polar covalent bonds. We talked the last time about showing Lewis structures or showing covalent bonds using Lewis structures. Well, now we're going to kind of define those bonds a little bit. So similar electronegativities, non-polar covalent bonds. Non-similar. So what on earth does that mean, non-similar? That means a little bit farther apart. Farther apart electronegativities are going to form polar covalent bonds. So that might not mean very much right now, but for an example, water forms a polar covalent bond. And that causes water to have lots of its characteristics that it does. So we have oxygen, hydrogen. Okay. So the electrons spend a lot more time around oxygen. It has a negative charge. And the hydrogen, and that's all due to electronegativity. The electrons spend a lot more time around oxygen because it's far more electronegative than the hydrogen. So that gives the hydrogen a partial positive charge on both of these, and that's that polarity. So like North Pole, South Pole business, okay? And then completely opposite, electronegativities will form ionic bonds. And we will come back to these in gross detail, but I really like the way the video says, uses our friends here, fluorine and francium. Fluorine will straight up steal francium's little electron out there, and then fluorine becomes negative, francium becomes positive, and causes that ionic formation. So these two would become ions, and they could be attracted by the positive and negative bonds there. Alright, the last kind of trend that we need to talk about today is ionization energy. So let's move up. And as you write that word, ionization, what do you think about? First, you should think about ion, which is a charged atom. In this case, we're going to talk about removing an electron. If I remove an electron from an atom, that means I have fewer electrons than I do protons. Okay, causing it to have an ion characteristics. It has a charge to it. So ionization energy is the energy it takes to remove an electron So this trend has a very similar pattern to electronegativity. Okay, so when we look at that, we're going to go up and to the right the same way that we did before. So we'll make that really clear, and then we'll talk about it a little bit. Again, an intuitive one, if you notice what we've talked about, ionization energy and electronegativity follow the same trend. Atomic radius is opposite. So that's really important. That's really important that you differentiate those. Electronegativity and ionization energy kind of go together, and we'll go back to our friends fluorine and francium. Okay, so now we will go back to our friends fluorine and francium for ionization energy. Ionization energy, let's consider francium. This little electron out here, is it going to take a lot of energy to snatch it off of francium? No, because francium's nucleus does not have the hold on this little guy out here. Fluorine, on the other hand, is holding on with all it's got, because its electron cloud is very close to its nucleus. It really badly wants that one electron so that it can have a electron configuration of like the noble gases. So it makes sense for the same reasons that electronegativity makes sense. Okay. Okay, so kinds of questions that you need to be able to do is put atoms in order of electronegativity or in order of ionization energy. So let's do an example right here in our notebook. We'll go put in order. Alright, so put these in order of ionization energy. We'll just grab some random elements. Okay, so that's probably a really bad example. I just looked across the periodic table, but first thing, if we look and we find, here's barium, here's cadmium, here's sulfur, and here's fluorine. So they're already in order. But what you need to match them up against the electronegativity. Let's pick a different set. That was a bad example. Alright, what if we do silicon, rubidium, molybdenum, and chlorine. Alright, That's a better example. If we look at silicon on the periodic table, silicon is over here. Okay. So we know that it has a pretty high ionization energy. Our next one was rubidium. Rubidium is way over here. So we know that rubidium has a lower ionization energy than silicon. Okay, but then molybdenum is right here. So our order would be rubidium, molybdenum, silicon, and then chlorine is on this side. So we would, answering this question, we would come and we would say rubidium is number 1, molybdenum is number 2. Then we look over here again at our periodic table. Silicon would be number 3 and chlorine is number 4 because we're following that trend. Okay.